Hi everybody, we're going to start our deep dive into data structures by looking at one of the most popular data structures ever created, and that is the array. As we're going to find out very shortly, we'll learn about what arrays are, why they are so popular, situations they're good in, as well as situations that they are not very great in, and a whole lot more. But before I go further, I should let you know that if you want a friendly yet comprehensive look at data structures and algorithms, including our friendly array over here, my book on this topic is just what you need. Look for it in any bookstore, real or virtual. So definitely check it out. But let's start by looking at arrays. I'm going to start at the very beginning. Let's answer the question of what is an array. So to explain what an array is, let's look at a real world example. Let's say that we want to have a list of groceries that we want to jot down. So here I have a lined notebook. I wrote down the words milk, eggs, cereal, salami, and juice in a sequential order. And these are kind of the items that I want to do. You probably create lists of things all the time, whether it's in your favorite note application, whether it's in an actual post-it note, or in any set of combination of things. Now, an array is a digital representation of lists of data that we might be creating. And so the way I look at it is an array is a data structure that is really designed for storing a collection of data. And the important part is this: storing a collection of data in a sequential order. That means that they are one after another available for us to look at. Now, from that very basic definition, let's look at common operations we'll use an array for, and that'll help us give a better picture of the full thing of what they do. Let's start by looking at what it means to add items to our array. So at a surface, the way we typically represent arrays is as a list of items, as a collection of items. Here you can see them that represented horizontally, where you have milk, eggs, cereal, salami, and juice. And we give our array a name. In this case, our array is called groceries. The way we reference an item in our array is by using something known as an index value. And this is a count or the number of the position that the array is currently in. And unless you're in, let's say, a language like Visual Basic, the typical convention is to start our counting for index values at 0. So you can see that you start our array, you have an array here, and at 0, 1, 2, 3, 4, at each of those positions, and an item is available. So at position 0, we have milk. At position 1, we have eggs. 2, we have cereal. 3, we have salami. And 4, we have juice. Now, if you want to add an item to our array, the easiest case is where we add an item to the end of our array. So here's an example where we add potatoes to our list of groceries, and you can see that it gets added, and we add an index item to go along with it. So now you have potatoes added to the end of our array, and we now have it located at index position 5. Pretty straightforward there. Now, there may be times when we want to add an item to the array that is not towards the end, but somewhere in the middle or maybe even the beginning. When it comes to inserting items into an array, it's a bit more of an involved process. So here, for example, I want to add an item called candy. I want to add it between cereal and salami, in between index positions 2 and 3. To add an item in the middle of our array, it requires me to kind of take all the items that are going to be coming after it and shifting them over. So salami, juice, and potatoes can no longer be at index positions 3, 4, and 5. They need to be shifted over, where now candy takes the position of salami, but index position of 3, and every subsequent item has a higher index position. So you can kind of see how the work involved to add an item to the middle or anywhere that's not the end requires taking into account every item that's going to be following it and readjusting its index positions. Earlier I mentioned that an array is a collection of items in a sequential order. The sequentialness, that's even a word, needs to be respected, needs to be maintained. And so you're always going to have a case where items will be increasing from 0 to the very beginning, sequentially to the very end, and that property needs to be maintained. You won't have candy, for example, appearing with an index position of 6 right in the middle between cereal and salami and have the current ordering be maintained. Every item needs to be reordered to take this into account. There's an important detail to keep in mind when we talk about the performance of an array when doing common operations like adding. Or our next topic, which is how do we remove items from our array. So we have, earlier we added potatoes to the very end. If we remove an item from the very end, it's a very straightforward operation. We just remove it, and our array just pretty much goes on with its life as it always has done. Now, when we have to remove an item that's not at the end, somewhere in the middle or somewhere at the beginning, the same idea we saw earlier when adding an item applies. The sequential order of the array needs to be maintained. So in this case, we're removing the very first item, milk. And when we remove that, it's not just removing the item from the beginning of our array, it also requires re-indexing every item as well. So for example, now that milk has been removed, eggs is the first item in our array, and it needs to have an index position of 0, which means every item following eggs needs to have its index position decremented by 1. So you can now see that removing everything causes eggs to now be at position 0, cereal to be at position 1, and so on. The next activity we'll often do with arrays, besides just adding and removing items, is searching for things in an array. With arrays, the common way, the road you travel on to find items is the actual index positions. You know that an array is going to start off at index position 0, and you're going to keep going until you run out of index positions. Now there's some helpful methods you'll find for like getting the length of an array, so you don't have to just go blindly, but for the most part you start at the beginning and you keep searching every item until you find what you're looking for. So for example, if I'm looking for salami, I wouldn't know exactly where to start, so I'll be starting with eggs, then saying if eggs is what I'm looking for. Nope. Is it cereal? Is it candy? Nope. Is it salami? Yes, it's salami. So after 4 operations, I now found where I am. And the longer the array, and if I'm looking for something towards the very end, I'm going to be looking at every item until I reach the very end. Something we'll be talking about much later on when we look at actually some algorithms is how can we optimize searching for an array. Now there are things we can do such as alphabetizing content that is more word-based, or arranging it by numerical values where it's sorted from like smallest to largest, where we can kind of reduce the size of the array that we're actually searching for. So if I'm looking for something that I know is going to be towards the end of the array, I can start my search towards the end itself as opposed to from the beginning. And you can see here's an example where we're just breaking the entire problem space of the array down into smaller and smaller segments. Binary search is a very common approach for being able to narrow down where you're searching, and we'll talk about that much later, but I just want to give you a heads up on multiple techniques available to make searching an array more intelligent. Now, to access an item from our array, this requires just our index position. So for example, if I want to access cereal, I just use groceries and pass in index position, and you'll get cereal directly added. Now this syntax is very common to say where you have the name of the array and then a bracket and the index position. Different programming languages, of course, have different approaches, but don't worry about programming languages or actual syntax for a language. Just think of it at a very high level, your mental model of it, that this is one way of being able to access an item in an array by just passing in the index position. So now that we've seen the basic operations we'll perform with an array and at a very high level how it works, let's talk about performance and memory, which is a very important part about how arrays typically work. Now let's talk about the average case and the worst case for common actions we'll be doing with our array. Now, as we saw earlier, an array is just a collection of items, which means that the amount of memory you take, it depends entirely on how long our array is. A very small array will take up a small number of items. A large array will take up a large amount of items, but it's going to be directly proportional to how large our array is. To access an item, the idea is that you just have the index position, so it's a constant type. You know exactly where the item is. Forget it very quickly. Insertion, deletion, all those items. If we're adding an item or removing an item from the very end, like we saw some of the examples, that's a constant time activity. You know, you go to the very end of the array, remove the item, everything is fine. If you have to remove it from anywhere else, on average, the worst case behavior is linear. You have a linear time operation because not only are you removing an item or adding an item somewhere in the middle, you then have to re-index and shift all the items that are following it back to where it needs to be in the right position to maintain the sequential property that our array needs to have. And linear search is how you search for an item from one side to the other. Let's say I'm looking for an item. In the case I was looking for salami earlier. I start at the beginning and just keep going down my array. If we do binary search, we divide our problem space in half depending on how smart our algorithm is, and that typically is a logarithmic activity on average. Worst case scenario, it's a linear operation. We'll look at that much later on as well, but take a moment to look at this table and just mentally walk through how we got these answers, and some of the examples I showed earlier highlight the average and worst case scenarios quite clearly. Now, The main thing to keep in mind, now that we've seen how arrays work, is that they are a fundamental data structure. This is why we're starting our look at data structures with the array, and almost all programming languages provide really good support for how they work. So both in my book and in the link I have below for the article, you'll see some examples of how in JavaScript we can work with arrays in great detail. And of course, if you have any questions, feel free to post in the forums at formnetcrypt.com, and below this video you'll see links to all the resources we've seen, both in this video and for ways to keep up with all the content that I will create. And with that, I will see you all next time.